Alright, good morning. Here we are for another lovely day of CENG 3306 Mechanics of Materials. Okay, so for today's first video, for lesson 30, we are going to learn about transverse shear stress. This is in section 7.1 and 7.2 of the Hibbler text, and we are going to go through a few lesson objectives today. 1. Explain the derivations, limitations, and assumptions inherent in the shear stress equation for bending. Calculate the quantity Q for a given cross-section. And calculate the transverse shear stress. So, without further ado, let us begin. And once I make sure I'm recording. And we are, everything's running, microphone's on, we are good to go. Okay. So, let us start. Alright, so let us do a bit of a review of bending first. Let us do a little bit of review over bending first. So I'm going to call this section Bending Review. Bending Review. Alright, so if we have a beam under, say, a linear or just a constant distributed load, like so, or like here, or actually, I'm going to show it with a cut. So imagine we have a beam with a cut. Method of sections, we have a beam with a cut, and there is going to be another piece of this over here. So we have cut this beam somewhere along its middle to analyze the internal forces within it, namely the shear and the moment. Now, of course, we can have axial force, but we're very familiar with that from our explorations of CAL members, so that should go without saying. Okay, then we have, say, an AY here, maybe a BY, and we have a linear force across the top of this, not a linearly increasing force, just a constant linear force, or a constant line load, probably a better way of expressing this, here. Or it could actually be just any kind of distributed load here. So I drew this as a constant function, but let's just say this could be any arbitrary W of x. And then inside the beam, we will assume when we initially draw this positive shear and moment according to this sign convention that we have discussed previously. And then finally, we will have an x, which is always measured from the left end of a beam. And then, actually, let me write this a little differently. I want to illustrate this as a delta x here. So we have an x and a delta x, where delta x is our little differential element that we have worked with many times and analyzed that's where we've done the previous drawings of plane sections, remaining plane, all that kind of fun stuff. Okay, and then review the assumptions. Let's do that. I have 6 assumptions that I want to keep in mind. So let me just call these 1, 2, 3, 4, 5, and 6. So we have 6 assumptions baked into the equations of bending that we have seen. And the first one is prismatic cross-sections. So in other words, you have a constant cross-section all the way across the beam. There are ways to analyze beams with non-constant cross-sections, but those methods are really methods of, I would say, a 400 level structural engineering course. They're a bit beyond the scope of this course. We're also talking about homogeneous, and I'm sure you could, and I shouldn't say only a structural engineering course. You can also have similar things in high-level mechanical engineering courses as well, of course. Something like a turbine blade would definitely be a non-prismatic element. 3, we can have linear. We're assuming homogeneous material. In other words, it's constant density, constant material. We're not having any weird holes in it. We're not just putting random chunks of aluminum in our steel beam, etc., etc. It's linearly elastic. So it's not a weird material, it's just a normal, friendly, happy, you know, Bob Ross, happy trees, happy material. Very simple. Something that would find its home in Mr. Rogers' neighborhood. Sigma is equal to negative my over I. That's what that comes from. Very nice, friendly, happy materials. Let's keep it simple. And not only are these nice, friendly materials, they also are within the, we're only loading them, so they're within the elastic range. So again, that is the assumption that allows for this equation. Although we have already seen in the previous two lectures, or the previous lecture, how to handle linearly elastic materials beyond their elastic range using the elastic plastic assumption. We're assuming that the E, the modulus of elasticity, is the same in tension and compression. What isn't necessarily true for certain materials. So this would go along with essentially this would essentially go along with your isotropic assumption, and we are assuming long, slender, straight beams. So we're not curving the beam. We haven't. We've kept architects far away from our analysis, so we're not doing any really crazy curvilinear beams. We're not doing any tapering beams. We're not doing really short beams. So this isn't just like a stubby beam that's only a foot wide for some insane reason. No, we're just, that there are cases where you actually do that for, I've seen those for things like very small pipe supports and things like that. But those need to be analyzed by other techniques, not by bending. See, these, really what you're assuming is that if you have, say, a point load, the point load has enough area to distribute that point load such that the point load assumption is valid. Again, if you think of a point load, it assumes that the load is applied at a single infinitely small point. In reality, this is physically impossible in terms of actual physical materials. If I could somehow magically apply a point load to any material, it would just go right through even the strongest material, because it had a true point load would have infinite pressure on the surface material. It just puncture right through it, go all the way to the center of the earth. But in reality, what we call point loads are something like, I like to think, my go-to example for a point load is, imagine you have a 20-foot long beam and you have a weight hanging from a chain that is draped around that 20. So say you have like a really long beam, maybe 20 feet long, and I maybe drape a chain or a metal cable around it, and maybe this cable is only half an inch wide or half an inch thick. Compared to the 20-foot long beam, this half-inch thick cable essentially has zero width. It is when you actually apply loads to real structures, you always apply them over an area. So in our shear diagrams, we will say that the shear will just instantly drop at the location of that point load. But in reality, if you were actually to very accurately model it, they actually do something kind of more like this, where they have a transition zone, or maybe more, if I exaggerate it, something more like this. There's a certain transition zone. Now, if the width of this is very small relative to the member, you can approximate this transition zone as a vertical load, which we usually do. But if your beam is very short, that point load assumption breaks down, and suddenly we have to analyze beams using other methods. So so when we design beams, we often are actually assuming impossible conditions. Just like in statics, you're assuming impossible assumptions like perfectly rigid materials, rigid bodies, things like that. But for certain analysis, it's actually perfectly fine. The key thing, there's nothing wrong with making, sometimes, that's the weird thing about engineering. Sometimes there's nothing wrong with making physically impossible assumptions, as long as you are aware of the background behind those assumptions and you know their limitations. So, but anyway, that's more the theory of engineering. Plane sections, of course, and our sixth assumption that you've seen before is that plane sections will remain plane. In other words, this can actually be approximated as small deformations. Okay. Next, let's see. Let us continue. Let me see something here. Okay, that'll work. So let us look at shear stress on a transverse plane. Let us look at shear stress on a transverse plane. Don't want that. Shear stress on a transverse plane. I cannot draw a straight line today. Shear stress on a transverse plane. Still looks like a monkey drew it, but a little better. Okay, you can go through, I don't know if we want to go through the full derivation, I don't know if we quite have time for that, but feel free to see the full derivation for this equation, if you are curious, on page 365 through 367 of the Hibbler text. This is where you'll find the derivation. Okay, and the formula for shear stress, this is going to be interesting. You'll see a quantity that we haven't seen before that we will learn how to calculate. Well, actually, you've probably seen it before. It's not that bad. T equals VQ over IT. Wow, doesn't this look like fun? Doesn't this look like loads of fun? Tau equals VQ over IT. Joy. Aren't you just giddy at figuring out what all these fun terms mean? Okay, well, let's do that. So we have tau. I shouldn't call it tau, it's tau, as I've explained. Capital V, this is a capital V. I'll just go down and do these all in red, or all these, I cannot see my colors. I'll do these all in blue. I and T. Okay, so let me define all of these. Tau is the shear stress on a transverse plane at the point of interest. Plane at the point of interest. Capital V is the overall shear force. This is what you get from your shear diagram. Shear force on that transverse plane. On that transverse plane. In other words, I'm talking about the plane of the cross section, really. Q is the first moment of outward area, and we'll talk about calculating this. First moment of outward area about the neutral axis. About the neutral axis. I is the area moment of inertia of the whole cross section. Moment of inertia of the cross section. And finally, T is, oh, that's fairly simple, is the cross-sectional thickness at the point of interest. And this works for any arbitrary cross-section at the point of interest. So, in other words, if I have an arbitrary cross-section here, let me draw a potato. for an arbitrary cross-section. So I just have an arbitrary cross-section. It could be something really weird like that. If I wanted to, we definitely need a weird integral to solve that. So let's hope we don't have that on the exam. Speaking of exams for the students taking the class this semester, I'm still working on grading the partial credit for exam 2. I'll have those up hopefully shortly. Now, let's see what's next. Yes, so this, let me show, so this is the cross section. Let me say, if you're familiar with, let me illustrate this maybe here. Let's say this is cut AA. If I have a beam, and let me draw a beam here, like this, an arbitrary beam, this would be the transverse plane I'm talking about. This would be cut A looking to the left or to the right. We're cutting it right through the beam and looking at the cross section, and this is what we see. And when I say an arbitrary point, what I'm saying is that I want the, so we have a cross section here, and I want the stress at some location here, or here, or here, just some arbitrary point. So this is the arbitrary point that we want shear stress. And in green, I'll say this is the cross section. So just the importance of terms. Okay. Now, so let's look at the Q. That's the one that requires the most, that's the one that's probably the newest thing you aren't the most familiar with, I should say. Q is defined as the first moment of outward area. First moment of outward area. First moment of outward area. Let's see here. Of outward area. First moment of outward area. And then, let's see, what is the definition of this? So Q is defined as the first moment of outward area. And then I will say, what's the formula for this? Well, Q equals the summation of Y bar A. Q is the summation of Y bar A. So, Y bar is Y bar is this, and A is this. Is the distance from neutral axis to the centroid of the outward area. To centroid of outward area. Outward area. Capital A is the outward cross-sectional area. And do be aware of this definition of outward. That's important. Outward cross-sectional area. And if you have a compound shape, we'll be used to looking at this for the outward word later, further on in further detail. Compound, Q is simply equal to the summation of the individual Q's if you have a compound shape. Okay? Q is simply equal to the outer shape. Okay? So, where is tau? Let us next consider where is the shear stress. Where is tau? Well, If we have a, well, obviously, we're going to have shear stress. Say we have shear stress here, a stress element. What we're actually going to solve for is this. And once you find one of them, we have all of them. So the equation is going to give us this one here. The equation will give us this one here, solve for this. Here. And then, since I know since equilibrium requires tip to tip or tail to tail, we'll know this one. Tip to tip or tail to tail. Okay. And so the overall state of stress for this bending shear stress will be like this. And you can do more circle on these if you wish. The state of stress. The state of stress on this is going to be like this. Let me draw a stress block. And then I want to work through a quick example of this. So the state of stress. Let me show you here. Now, the state of stress on at least on the main element, the globally oriented element, globally XY oriented element, is going to be like this. Obviously, you can have different states of stress if you take different cut planes, like here and like here. And this stress block that I am drawing is assuming that you have only strong axis bending. What that means is, say we're loading it only with vertical loading. If you're putting loading along the top of the beam, that would be you'd have only bending along one axis. If I apply a horizontal loading to a beam, then I would have moment in the other direction as well. So I'd have moment like this, or I would have bending stress like this. So this sigma is going to be my over I, and this tau is going to be equal to VQ over IT. So let me work through an example of calculating this. So essentially the way this works is for Q is the difficult part. Q is basically calculated based upon the area above the point that you're interested in. Q is based on finding, when I said the outward cross-sectional area, what I'm really talking about, at least for upward loads, is at least for downward loads, regular bending, it is based upon the loading or the area above where you're interested in stress. And later on we'll learn about shear stress distribution throughout a beam. Okay, so let me work through an example here. Example. So I am given information about the cross-section, and I am also given that the shear loading out on this cross-section is 50 kips. I'm not trying to actually see and this isn't a design or full analysis example. All I'm trying to do is determine what the actual shear stress is at different points. So I'm going to have a simple rectangular beam. Today we're trying to keep it kind of simple. Just nice, friendly examples, friendly beams. You don't get much more simple than a rectangle. Okay. And this beam is going to have a width of 4 inches and a height of, let's say, 6 inches. All right. Now the neutral axis will be located here, right at the middle. For a rectangle, it's nice and symmetric. We don't have to worry about it. The neutral axis will be located right at the middle. And let me also define a point B. Point B will be located 1 inch from the top. point B will be located 1 inch from the top. I'll need to know that as well. 1 inch. Okay, I want to find two things. Find A, the shear stress at neutral axis, so taw at the neutral axis, and B, the shear stress, or sorry, this taw at B, I should say. Okay, so let's do that. This one will be a fairly quick example because honestly, usually shear stress isn't that bad unless we have really complicated examples, which we can, so we'll see. Okay, so let's do part A first. Let me work through that. Find the shear stress at neutral axis. At the neutral axis. All right, so I am going to draw the beam and I'm going to show the, I'm going to draw it and be cognizant that we're interested for the calculation of Q in the portion of the beam above the point that we're interested in the stress at. So here's the neutral axis here. The outward first moment of area is going to be based upon this area. And the reason for that fundamentally is that when you have a shear stress applied downward, when you have a shear stress applied downward, or sorry, a shear load applied, or a vertical load applied downward, your the area above it is actually helping to decrease the well, actually, let's think about that. Anyway, it relates to how much area you have above or below. That will help decrease the stress there, because by the time you get to the neutral axis, some of the load has already been carried by the by that there. Okay, so maybe that's not the best way to explain it. Maybe I would more say it's actually the more area you have below, the lower the shear stress will be, but that's okay. Or the less area you have above, the higher the shear stress will be for normal bending. I think that makes a little bit more sense. Okay, so we're going to need the Y bar for this area, and that distance, this Y bar, since the whole thing is 6 inches, the Y bar for just the outward area here is 1.5 inches. And of course, we have the same overall dimensions. This is 3 inches, 3 inches, and 4 inches here. And 4 inches. And then taw is going to be equal to, taw equals VQ over IT. And so Q is based upon just this portion above the point that we're interested in. That point is the neutral axis. This point is just the centroid. That's going to be the Y bar. But I, the moment of inertia, is based upon the entire section. So this is going to be equal to IX, which equals 1/12 times just BH cubed over 12, 1/12 times 4 inches, times 6 inches to the third equals 72 inches to the fourth. Not a hard calculation. Okay then. So that's, oh wait, I wrote that totally wrong, sorry. Dope. V is not equal to IX. That's just something else, sorry. Did not need an equal sign there. T is equal to 4 inches, and V is equal to 50 kips. The T is the thickness at the point of interest, which is here, and it's the same thickness as the rest of the beam, which is 4 inches. So I need to find Q. Well, it is simply equal to Q equals Y bar A, which is just 3 inches. That is the, let's say the, actually let me write it in different order first. Let me actually write it Y bar first. Y bar here is 1.5 inches. It is the the centroid of the area above, times the area, which is just a rectangle, so it's nice and simple, nice happy formulas today. 4 inches times 4 inches times 3 inches, I know how to calculate the area of a rectangle, equals 18 inches to the third. And then finally, I can complete the calculation by finding tau. Tau is going to be equal to 50 kips, the V, times the Q, 18 inches to the third, over I and T, which are going to be 72 inches to the fourth, times 4 inches. And if we think about this, we have inches to the fifth, inches to the third, inches to the fifth in the denominator, 4 times 1, or 4 plus 1, and inches to the third in the numerator, which means we'll get kips over inches squared, or KSI, which is exactly what we expect. So this comes to 3.13 KSI. KSI. Yay, joy. Okay. Here, let's see. Now let's look at part B, or where we find the stress at point B. And I should actually rephrase this. I kind of said that the stress will be higher the lower you are in the beam. I should rephrase that. I should really say the further you are from the centroid, the further you are from the centroid, the lower the shear stress. In other words, the shear stress will tend to be maximum at the centroid. If we were calculating the first moment of area for a point at this location, I would actually go and use the area below here. So if I was asked for the stress at this location, I would use the first moment of area down. So it's actually based upon the area below. Okay? Hopefully that makes sense. Okay. So then, again, it's based on what I might say, it's whatever going up or going down would result in the smallest Q. That is the one you'll calculate. So point B, hopefully that is clear as mud. Point B, we're trying to find the stress, the shear stress, at a point 1 inch below the top of the beam. So I have a situation like this. Let me draw this out. And this is then like so. My neutral axis is still way down here. Well, if we call the middle of the beam way down here, but I guess relatively speaking. Point B is here. 1 inch from the top. But then here, let's see. You know what? Actually, I don't have enough room to draw this, so I'm going to purposely not draw this to scale. Oop, I didn't mean to erase that, but nope, it's gone. Okay, oh well. You know what? Let me just draw this whole thing a little bigger so I have enough room to really draw what I want to draw. Didn't get the time for that. So let me draw this a little bit bigger. Here. Like so. And we have the neutral axis here. The neutral axis here. Then point B, I can just draw it I'm going to draw it here. And that is a distance 1 inch from the peak. Or 1 inch from the top of the beam. 1 inch from the top of the beam. Here. And so we're going to base our Q off of the outward area. Again, if I was asking for the stress at this location, I would actually base my Q off of the area downward. It is based off the minimum Q. In other words, look at this and say, what is the distance to the closest, which direction does the closest surface lie, and calculate the, closest vertical surface lie. And, this is a vertical surface. I got to be very careful with my language. If you're closer to the top of the beam, take it upward. If you're closer to the bottom of the beam, take it downward. There, that makes sense. Maybe not the most technical way to describe that, but hopefully that is a little clearer. Okay, so then I am going to need the center of this, or the centroid of this region for this Q, and this is the Y bar we're going to use. So Y bar is going to be 2.5 inches. And so now, thankfully, we don't need to recalculate I. It's going to be exactly the same. So the only thing that's actually changing is Q. 1 inch. Actually, you know what? I still like using the Y bar A formula. So let me do that. Y bar is going to be 2.5 inches. And the area is going to be 4 inches times 1 inch here. And this is going to be equal to 10 inches to the third. And so simply Ta then is going to be 50 kips times 10 inches to the third, our Q. So it's VQ over IT over our I, which is 72 inches to the fourth, times the thickness, which is just 4 inches. And then this comes to a final answer of 1.74 KSI. So we can see that the shear stress is remarkably lower than the shear stress of the neutral axis. In other words, as you move further from the centroid, the shear stress tends to decrease. There may be some weird exceptions to that rule. Maybe if we really dug into the math, we could contrive an example that didn't apply. But generally, if you have a normal shape, in almost all shapes, the shear stress will tend to decrease as you travel away from the neutral axis. All right, that will do it for this lesson. This one will be fairly quick, but the next one, lesson 32, will be a bit longer, and we're going to go into calculating Q and shear stress for a few more complicated examples. All right, that'll do it, and as always, thank you.